Welcome to the Deep Dive. We're here to distill complex ideas into clear, actionable insights for you. Today, we're diving into something absolutely fundamental to calculus, functions, our mission. To unpack Chapter 1 of Stewart, Clegg, and Watson's calculus, early Transcendentals, pulling out the crucial insights, making them engaging, and really clear for you.
And it's a vital chapter. Honestly, it sets the stage for everything else in calculus. We're talking about the core ideas, what functions are, how we graph them, how we can transform and combine them. It's the groundwork.
Okay, let's kick things off right at the beginning then. What exactly is a function? At its heart, it seems like a rule, right? A rule that takes an input from a set, the domain, and assigns it to exactly one output in the range.
Exactly one. That's the critical part. Think of it like a perfectly reliable machine. You put something and call it X, and you get one specific thing out, Fx or Y. No surprises.
Right, and X is the independent variable because we choose it, and U depends on it. Does this machine always deal with numbers, though? Oh, not at all. That's the beauty of it. While we often use numbers, the core idea is just that predictability. One input, one definite output. And the textbook highlights four really useful ways to think about or represent a function. Each gives you a different angle.
Okay.
First up, algebraically, with an equation, like the area A of a circle is A or R2. Give me the radius R, I can tell you the exact area A. Super precise.
That precision is great, but sometimes maybe a list is better, like a numerical way.
Exactly. A table of values. The book uses world population P versus time T. So like in 1950, P was about 2.56 billion. There might not be a neat formula, but that table is the function. For each year, one population figure.
Got it. And verbally, just using words.
Yeah, like the cost C to mail something, it depends on weight W. Maybe it's $1 for the first ounce plus 15 cents for each extra ounce. No formula, but the rule is perfectly clear.
And finally, visually, with a graph. Think about earthquake data. A geologist sees the ground acceleration A versus time T. Just looking at the graph, they instantly get a feel for the shaking, the peaks, the patterns. Sometimes a picture tells you more, faster.
That makes a lot of sense. Different tools for different jobs. So with graphs, is there a quick way to check if some curve actually is a function?
Yes, there is. It's called the vertical line test. Super simple, super useful. Just imagine drawing vertical lines across the graph. If any vertical line hits the curve more than once.
Then it's not a function.
Exactly, because that would mean one input X has multiple outputs Y, which breaks the fundamental rule.
Makes sense.
We also run into functions that use different rules for different parts of their input domain. We call these piecewise-defined functions. The absolute value function, X, is a classic example.
When it's X if X is positive or 0, and X if X is negative, gives it that V shape.
Precisely. And functions can also have symmetries. We talk about even and odd functions.
They're like by 2 being even.
Yep. Even functions, like by 2, are symmetric across the y-axis.
Yes.
So fx is the same as fx.
Right.
Folded on the y-axis, that matches up. Odd functions, like by 3, have origin symmetry.
Yeah.
fx equals fxx. It's like a 180-degree rotation.
And this isn't just about looks.
Not at all. These symmetries often show up in physics, engineering. They reflect underlying principles. And practically, they can make calculations way easier down the line. Oh, and we also talk about functions being increasing graph going up from left to right or decreasing graph going down. Basic, but key for describing change.
Okay, so we know what functions are, how to picture them. Now, how do we use these ideas to model the real world? This feels like where it gets really interesting. The idea of a mathematical model. What's the gist?
Right. A mathematical model is basically a mathematical description, often a function or an equation, that represents some real-world phenomenon. The process is usually iterative. You formulate the problem mathematically, you apply your math tools, you interpret the results back in the real world, and then you test it. See if it holds up.
But it's not a perfect copy of reality, right?
Yeah, definitely not. Models are idealizations, simplifications. But a good model is accurate enough to give you valuable insights, help you understand what's going on, and even make pretty decent predictions.
So what kinds of functions do we use for this modeling? Let's start with linear models. Y equals mx plus b.
Yep, the simplest kind. Their key feature is a constant rate of change, that m, the slope. The book gives that example of dry air cooling as it rises. Maybe temperature T equals dense 10 hour plus 20. Age is height in kilometers. That netacant 10 means it cools 10 degrees Celsius for every kilometer you go up. Constant rate.
We also saw it used for CO2 levels, and that brought up interpolation versus extrapolation.
Interpolation is estimating a value inside the range of your data. Like if you have data for 1980 and 1990, estimated for 1987. generally safer.
But extrapolation is predicting beyond your data, like for 2025. That seems riskier. What stands out to you about those risks?
Oh, it's definitely riskier. The further out you go, the bigger the gamble, because you're assuming the trend, that straight line, just keeps going exactly the same way. Real-world systems often change. Maybe policies shift, technology improves, or some limiting factor kicks in. Relying too heavily on extrapolation, especially far out, can lead you pretty far astray.
Yeah.
It's an educated guess, but the uncertainty grows fast.
Okay, good point. So, beyond linear, we have polynomials.
Right. These involve terms like by 2, by 3, etc. Whole number powers. Degree 1 is linear. Degree 2 gives you quadratic functions.
Their graphs are parabolas.
Right.
Yes.
Always parabolas, yeah. The book uses a great example, dropping a ball from the CN Tower. The height over time to Kuyesh might be something like h is 449.36 plus 0.96 t 4.90 t2. That quadratic model fits the physics pretty well.
And you can use it to find when the ball hits the ground.
Exactly. Just set h to 0 and solve the quadratic equation for t. Polynomials are really flexible for fitting curves to data.
Then there are power functions, fx, all a say.
Yeah, where a can be various things. If a is a positive integer like n, you get those polynomials we just mentioned. By 2, by 3, by 4. As n gets bigger, the graphs get flatter near 0 and steeper elsewhere. If a is a fraction like 12 or 13, you get root functions square root, cube root.
Okay.
If a is -1, you get the reciprocal function, fx equals 1x. Its graph is a hyperbola. This pops up in physics, like Boyle's law for gases. Volume is inversely proportional to pressure, V equals Cp.
And if a is -2, fx equals cx2.
That's the inverse square law. Super important in physics. Think illumination from a light bulb, it drops off with the square of the distance. Or gravitational force or electrostatic force, same mathematical form.
Wow, that structure appears a lot.
It really does. We also briefly mentioned rational functions, which are just ratios of polynomials, and more broadly, algebraic functions, built using standard algebra operations.
Okay, so those are all built with algebra. Then we get to the transcendental functions. What makes them different?
They transcend algebra. You can't build them just using addition, subtraction, multiplication, division, and roots. The big ones are exponentials, logs, and trig functions.
Let's start with exponential functions. Fx equals bx.
These are the functions of rapid growth or decay. Their defining feature is that the rate of change is proportional to the current amount.
Like population growth.
Exactly. Bacterial growth, world population sometimes. The book might use a model like PT equals T0, 1 plus RT, or radioactive decay, where stuff disappears at a rate proportional to how much is left. The book mentions viral load decline too. V equals 0 decay factor.
And that paper folding thought experiment really hits home how fast exponential growth is.
Doesn't it? 50 folds, and you're talking millions of miles thick. It's mind-boggling and essential for understanding things that grow explosively. Within exponentials, there's one that's absolutely central to calculus, the natural exponential function, yx.
Where e is that special number, about 2.718.
That's the one. So why is he so special in calculus? Well, it has this unique property. The slope of the tangent line to its graph at any point is equal to the value of the function at that point.
So its rate of change is equal to its value.
So precisely. At 0, 1, the slope is exactly 1.
Yeah.
This property, ddx xx, makes calculus with E incredibly elegant and simplifies so many formulas involving continuous growth and decay. It's the natural base for these phenomena.
Powerful stuff. And the flip side of exponentials are logarithmic functions, fx, off x, log x.
They're inverses. They undo exponentiation.
Yep.
If by xx, then log bec x equals y.
Yeah.
Essentially ask, what power do I need to raise the base b to in order to get x?
And the most important one is the natural logarithm, ln x, which uses base e.
That's the one. Super useful for solving exponential equations or for dealing with quantities that span huge ranges of values. Think pH scale, Richter scale, those are logarithmic.
Okay, and the last big group of transcendentals, trigonometric functions.
Sine, cosine, tangent, and their relatives. Their key feature is periodicity. They repeat in cycles.
Which makes them perfect for modeling things that repeat.
Exactly. Tides going in and out, a spring bouncing up and down, sound waves, AC voltage, anything cyclical.
And you mentioned using radian measure is crucial here.
Absolutely critical in calculus. Using degrees messes up the derivative formulas. Radians keep things clean and mathematically natural.
Okay, we've covered a huge amount of ground. We know what functions are, the different tarps, how they model the world. Now, how do we start manipulating these? Building new functions from the ones we already know. Let's talk transformations.
Right. This is like having a basic toolkit of function shapes, lines, parabolas, x, sine waves, and learning how to move them around and reshape them. First, shifts. Vertical shifts, y, fx plus c. Just move the graph up or down. Horizontal shifts, y-f(x)(c), move it left to right. Remember, it's xc for a shift right by c.
A little counterintuitive on the horizontal one?
It is a bit, yeah. Think of it as needing x to be c units larger to get the same input into f as before.
Okay, so if I have yx2 and I want yx plus 3 plus 1.
You take the basic parabola, shift it 3 units to the left because of the plus 3, and then 1 unit up, boom, new graph.
And we can stretch or shrink them too.
Yep, vertical stretching shrinking comes from multiplying the outside, y equals c fx. If c1, it stretches vertically. If 0, c1, it shrinks. Horizontal stretching shrinking involves multiplying the inside, y equals fcx. Here, if c1, it actually shrinks horizontally. If 0, c1, it stretches. Again, a bit counterintuitive.
And flipping them over.
Easy ones, easy ones. Y equals ffx reflects the graph across the x-axis. Y equals fx reflects it across the y-axis.
So it's like a whole graphical toolkit.
Exactly. And we see it used practically like modeling daylight hours.
Yeah.
The book shows LT 12 plus 2.8 sin to 365 T80 for Philadelphia. That's a basic sine wave that's been shifted up, average 12 hours, stretched vertically, amplitude 2.8 hours, had its period adjusted to 365 days, and shifted horizontally to match the seasons. Real-world modeling often involves these transformations.
Beyond moving one function around, we can also just combine them with arithmetic, right? Add, subtract, multiply, divide.
Sure can. F plus g, x is just fx plus gx. Same for subtraction, multiplication, division, though you have to watch out for dividing by 0. The domain of the combined function is usually just where both original functions are defined.
Okay, simple enough. But then there's composition of functions. F circle g. What's happening there?
This one's really important. It's about feeding the output of one function into another function as its input. So FOGX means FGX. You calculate GX first, get an output, and then plug that result into F.
Like a production line.
That's a great analogy. Output of machine G goes into machine F. If FX equals by 2 plus 1, then FGX means F by 2 plus 1, which is F by 2 plus 1, which is 42 plus 1. Being able to compose functions and also to decompose a complicated function into simpler composed pieces is a really powerful skill in calculus.
So if we can build functions up, can we run them backwards, undo them? That sounds like inverse functions.
Precisely. An inverse function written F1, that next one is not an exponent, reverses the action of F. If F takes a 2b, then F1 takes b back to a.
But not all functions can be reversed, right?
Correct. For a function to have an inverse, it must be 1-to-1.
Meaning
Each output y comes from only one unique input x. No two different inputs can lead to the same output.
And we can test that visually.
Yeah, with the horizontal line test. If any horizontal line crosses the graph more than once, it's not 1-to-1, and it doesn't have a true inverse over its whole domain.
Like y equals by 2 fails that test.
Exactly. Both x2 and x2 give y4. So if you try to invert it, where does y4 go back to? 2 or negative 2? Ambiguous. But y equals by 3 is 1-to-1.
Okay. So if it is 1-to-1, how do you find the inverse?
Algebraically, you write y if x, then you solve that equation for x in terms of y, then you swap the letters x and y to get the conventional y equals f1x form. Visually, the graph of f1 is always a reflection of the graph of f across a diagonal line yx.
And conceptually, it just undoes f.
Perfectly. If fx equals by 3 plus 2, cube, then add 2, its inverse is f1x, cube root by 2, subtract 2 and take the cube root, opposite operations in reverse order.
And quickly, inverse trigonometric functions like arcs and x, why do they have restricted domains?
Because the original trig functions, like sin x, cos x, are definitely not 1-to-1. They repeat endlessly. They fail the horizontal line test spectacularly.
So we have to chop them down.
Exactly. We restrict the domain of, say, sin x to just minus 2, 2. On that interval, it is 1-to-1, so we can define a unique inverse, arcsin x or sin 1x. We do similar things for arccos and arctan.
Got it. So wrapping up, we've really journeyed through the world of functions today. From the basic definition, that predictable rule, to seeing how different types, linear, polynomial, exponential, trig, act as powerful models for understanding reality. We've seen how to transform them, shift, stretch, reflect, and combine them through arithmetic and that key idea of composition.
And finally, how to reverse them with inverses, provided they pass that 1-to-1 test.
These really do feel like the fundamental objects, the basic building blocks we'll be working with throughout calculus.
They absolutely are. You can think of this whole chapter as building the essential scaffolding. Understanding functions deeply is what allows us to then effectively tackle rates of change, find maximums and minimums, calculate areas, all the core concepts of calculus that come next. It's the language we use to connect the abstract math to concrete problems everywhere: physics, engineering, economics, biology, you name it.
So to leave you with something to mull over,
Yeah.
think about that stark contrast between the natural exponential function yx and its inverse, the natural logarithm yonx. It just explodes upwards. It hits a million when x is only around 14. But ln x grows so slowly. In fact, it grows slower than any positive power of x, like x 0.001. This extreme difference, the explosive growth versus the incredibly slow, creeping pace, really hints at fundamental limits and behaviors you see in nature, in economics, everywhere. It's a tension that calculus helps us quantify and understand, and it only gets deeper as you explore more. Thank you for joining us on this deep dive.